So hello everyone, welcome back to our YouTube channel. In this video, I'm going to discuss about different types of stainless steel. In last video, I discussed about tool steel, in which I discuss high speed steel. In this video, I'm going to discuss about stainless steel, different types of stainless steel. So let's get started. So in last video, I showed you this flow chart or a diagram in which we discussed this one, tool steel. In this video, we are going to discuss about stainless steel. And one thing you should remember about stainless steel is that chromium percentage should be always greater than 10%. If your chromium percentage is not greater than 10, then that steel is not called as stainless steel. So you have to remember this thing. Chromium percentage should be greater than 10%, then only it is called as stainless steel. So there are different types of stainless steel, and what I have done in this video, I have divided each steel into these five parts: composition properties, heat treatment, structure, and uses. So first I'm going to discuss about composition and structure. So let's get started. So these two are very important and highly used stainless steel in our daily life. First one is austenitic, second one is ferritic. So austenitic stainless steel name itself saying that we have austenite. Austenite is nothing but FCC crystal structure, phase which is there in iron carbide phase diagram. So this is the austenite phase. You can see it is stable at or above 727 degrees centigrade. So austenite it's stable above 227 degrees centigrade, and this one is austenitic stainless steel, in which you can see the composition of chromium is very high, which is around 16 to 26 percentage, and nickel is around 6 to 22 percentage, and crystal structure is FCC, and it is stable at room temperature. Just now I told you that austenite is stable above 7 to 7 degrees centigrade. Then how does it stable, or how is it stable at room temperature? So what we are going to do, we are going to add stabilizer. So to stabilize austenite phase, we add gamma stabilizer. Gamma stabilizer, as I've shown in this, nickel is the example of gamma stabilizer. So nickel stabilize this gamma phase by forming solid solution. So as we know, nickel is FCC crystal structure and austenite is also FCC crystal structure. So they form solid solution, and due to the formation of solid solution, the gamma phase, which is austenite, it stabilizes. So it stabilizes at room temperature, at 25 degrees centigrade at room temperature. So that's the reason we have austenitic stainless steel, which is stable at room temperature due to presence of gamma stabilizer. So what it does, it decrease this line. This line is 727 degrees centigrade. It decrease this line to room temperature, 25 degrees centigrade. So this happened because of gamma stabilizer. Gamma, gamma stabilizer. Example of gamma stabilizer is nickel. Okay. Similarly, in ferritectic stainless steel, the name itself is saying ferritectic means alpha iron, which is BCC crystal structure, and composition is here. Chromium is around 12 to 18%, and nickel is like either you have nickel or either you don't have. So very low to no nickel, and BCC is stable at all the temperature. So similar, we to stabilize this peritectic stainless steel at all the temperatures, we add chromium, and chromium acts as a alpha stabilizer. So it's act as a alpha stabilizer, chromium. So chromium is BCC crystal structure, and iron, which is alpha iron, it is also BCC crystal structure. So both form solid solution, and that solid solution stabilizes the alpha iron at all the temperature. So that's why ferritectic stainless steel is also stable at all temperatures, and FCC is stable at room temperature. So that's the reason of the stabilization. Here the reason is gamma, and here the reason is alpha stabilizer. And the important thing is the percentage of chromium. Here you can see percentage of chromium is very high. So austenitic stainless steel has very good corrosion resistance as compared to ferritic stainless steel. So that thing is important. So let's move further. Yeah. So far I discussed about composition and structure. Now I'm going to discuss about heat treatment. So first we need to understand what is heat treatment. So heat treatment is nothing but heating, soaking and cooling. So this is temperature versus time heat cycle. First we heat the material at certain temperature by increasing the temperature. So as you can see, we are increasing the temperature linearly. Then we soak this material for some time at the same temperature. So temperature is same, but time is increasing. So you can see x-axis is time, y-axis is temperature. So time is increasing and then we cool it. This is known as cooling. So depending on the cooling rate, depending on the depending on the cooling rate, we have different types of heat treatment. First one is annealing. Second one is normalizing. Third one is quenching. So annealing is very slow. So when the cooling rate is very slow, then the process is known as annealing. This process is also known as not air, furnace cooling. Furnace cooling. So cooling in this process is also known as furnace cooling. While in case of normalizing, if we increase the cooling rate a bit, then then that heat treatment is known as normalizing, where the cooling rate is a little bit higher than annealing, but lesser than quenching. And the cooling is also known as air cooling in the normalizing case. So air cooling. And quenching is rapid cooling, where we cool the material very quickly, very fast. So that process is known as quenching, which leads to the formation of martensite. So in case of steel, what we are doing, we are having alpha iron, which is stable at room temperature. Let me erase all the things. Yes. So in case of steel, we have alpha stabilizer, not alpha stabilizer. We have alpha iron, which is BCC crystal structure. What we do, we convert this BCC to FCC by heating the material, by heating above 727 degrees centigrade, where austenite is stable, right? Where austenite is stable, and then we cool it to form BCT structure. BCT is body center tetragonal, to form BCT structure. So this is what we are doing in steel. We convert BCC into FCC and then FCC into BCT. And BCT is nothing but martensite, which is very hard. So this is how we increase the hardness. This is how we harden the material with the help of heat treatment. So first we have alpha BCC, then FCC, and unstable FCC is get converted into martensite, which is known as BCT. So let me show you this diagram again. In this diagram, first we have alpha. Okay, this one is alpha iron. We heat it above 727 degrees centigrade to get gamma phase. Why we do this thing? So BCC to FCC, we heat the material. So the distribution of carbon is very good in case of FCC. The carbon get distributed evenly throughout the crystal in case of FCC. That's why we heat the material to get FCC crystal structure and we cool it again. So while cooling below 727 degrees centigrade, gamma become unstable and it forms BCT. And BCT only form when we cooled it rapidly, which is nothing but quenching. When we perform quenching, then only we will get BCT crystal structure, which is nothing but martensite, which harden the material. So that is the simple thing we are doing in case of steel. So this is the heat treatment. So when it comes to austenitic stainless steel, we cannot perform this heat treatment because austenite FCC is stable at all the temperature. And as I told you earlier, to convert FCC into BCT, we need unstable austenite. But because of gamma stabilizer, it is very difficult to have unstable austenite. That's why we cannot harden this material with the help of heat treatment. So we can hard we can harden this material by using cold working, by doing some cold work. So this is the cold working where we uh, where we stick the material or we pass the material between two rollers which are moving in opposite direction, and we elongate the grains into a particular direction. You can see the grains are elongated. So in that direction, hardness increases. So this is the one way to increase the hardness of austenitic stainless steel. But we cannot perform heat treatment. Why? Because as I told, high stability of FCC phase due to gamma stabilizer, and to form martensite we need unstable austenite, and that is difficult in this case. Similarly, in ferritectic stainless steel, as I told you, for steel we convert BCC into FCC, but because of alpha stabilizer, BCC is stable at room temperature, so it will not convert to FCC. If you are not able to convert the FCC, we don't have even distribution of carbon throughout the crystal structure. So that's why we can't get martensite again. And if we don't have martensite, we cannot harden this material using heat treatment. So again, we have to go to cold working or some other process to increase the hardness of the ferritic stainless steel. So that's the heat treatment in both the stainless steel. And these are some unique properties of stainless steel. First one is austenitic stainless steel, which is highly or most corrosion resistant family of stainless steel. As I told you, due to high percentage of chromium, the corrosion resistance of austenitic stainless steel is very high. So this one is very important point. And this one is non-magnetic as it is austenite. So austenite is non-magnetic, and it has excellent formability and weldability. So we can mold it into any shape because of this formability. And as I told you, it cannot be hardened by heat treatment, only by cold working. So these are some unique and different points about austenitic stainless steel. Similarly, in case of ferritectic stainless steel, it is magnetic, lower nickel, so most cost effective. And as I said, chromium is there, so it acts as a alpha stabilizer. And lower nickel means we don't have any gamma stabilizer. Like so that's why FCC is not stable. BCC is stable. BCC is stable because of alpha stabilizer. So it has moderate corrosion resistance and especially to stress corrosion cracking. And as I told, cannot be hardened by heat treatment because BCC is very stable. So we can't convert BCC into FCC. So we will not be having BCT crystal structure to increase the hardness. Further, some of the things are remaining like uses. These things I have discussed. Heat treatment also I have discussed. Uses I will discuss in next video. And in next video, I'm also going to discuss about uh, three more types of stainless steel. For example, martensitic, duplex, and precipitation hardening stainless steel. So in next video, I will discuss these three. As the video length is already gone to 14 to 15 minutes, so I don't want to increase it more. So that's all from my side in this video. Thank you for watching. Stay tuned. See you in the next video.